Okay, let's start. Welcome everybody, big crowd, so that's a good thing. Today I'm going to talk about everything but PHP. I'm going to talk about paradoxes and theorems every developer should know. So it's a bit about math, a bit about science. Now, fortunately, I'm not a mathematician or a scientist, so I keep things relatively simple. Well, simple, we'll do some quantum mechanics, but relatively simple. So what I'm going to do is I'm going to present some theorems and I'm going to show you how it relates to the things that we do in our daily development basis. Okay, so let's start. And let's start with the German tank problem. Has anyone heard about the German tank problem? Okay, some people have already seen the talk. They lost the war, yeah. Now the thing is, the German... So yeah, there was a problem with the tanks. Actually, it's not about the Germans per se, so don't blame them. The thing is, suppose I have a war and there are tanks. So what you want to do is if you have a war against tanks, one of the things you want to know is how many tanks does my enemy have? Because if they have only one tank, I can beat them. If they have 1,000 tanks, I probably run away the other way. So you want to know how many tanks does the enemy have. Unfortunately, you cannot look this up at Wikipedia, especially not in the Second World War. So there's no way of knowing how many tanks the enemy have. Now, let's take a look at the German tank. I guess it's something like this. And tanks and pretty much everything we have in our daily life has some kind of way to identify the actual thing, the actual object. So in this case, it's a tank and it has a tank with a number 15. Is there anything we can conclude from this? Can we conclude that the Germans have 1,000 tanks by just seeing a single tank? No. Can we conclude that they have 4 tanks? Maybe it's more likely than 1,000 tanks, right? Can we conclude that they have at least 1 tank? 400% sure. Well, tank, sort of. Now, let's go to a battlefield. And these are the Swiss, no, not the Swiss Alps. That's not really French Alps. And this is a battlefield. And on the battlefield, we see 4 different tanks rolling up. What can we conclude here? Can we conclude that there is at least 1 tank? Yeah. 4 tanks? Yes. 1,000 tanks? Still not. But what we can do here is we can see that they all have different identification numbers, 15, 72, 53, 8. Now here's the thing. Statistician says there is a formula, namely this. N is sort of kind of m plus m divided by k minus 1, where m is the largest number, the largest identification we saw, and k is the number of elements, the number of tanks, 4 in this case. If we fill this in, we get 72 plus 72 divided by 4 minus 1 is 89. So by the fact that we saw a tank with identification 72, plus the fact that we saw 4 tanks, we can say most likely there are 89 different tanks just by seeing 4 tanks. Does that make any sense? No. But actually it does. Because what happened in June 1940, the Allied intelligence estimated that there were about 1,000 German tanks. Statistical analysis by using that formula says, well, considering the number of identifications, tanks identified and the number of tanks, we conclude that there is only 169, so a far less number. The actual number was 122. So I don't know what kind of gambling they use with the Allied intelligence, but it's way off. 1 year later, 1941, they estimated 1550. And statistics says, well, we saw more number of tanks, we saw different identifications, we estimate 244. In reality, there were 271. So that's pretty close by just filling in some numbers. Again, 1 year later, they said 1515 again, so I think Allied intelligence just stopped caring or something, I don't know. Statistics says, well, we think 327. In fact, 342, so that's really, really close by. That's almost spot on. by just looking at tanks, number, identification and number of tanks. What I tried to tell you is that there is data leakage everywhere. We leak data without knowing that we are leaking it. For instance, user IDs, invoice IDs. How many of you use a MySQL database? Sorry. How many of you use auto increments? How many of you leak auto increments to the outside world? There you go. This actual formula is used to approximate the number of iPhones sold in 2008. They just got on the internet and said, give me your iPhone identification number, where you bought it, what year, etc. And they approximate the number of iPhones sold in 2008, and it was pretty close by. What I do, or what I've done, every month I get an invoice from a SaaS company I have a subscription from. And I noticed that every month the invoice number increases. So in July of the first month I got a number, August a higher number, etc. And every year that number resets. So I put that numbers all in columns like this. And what I've done, I've taken the differences between those numbers. So August, between July and August, is a difference of 6,725. In September, it's increasing. So every time it's increasing. What I can do is I can deduce by this that the number of subscription that the company has is actually increasing. Because if it's increasing, I get more, the difference will be higher. So every time the difference will be higher. If I put this in percentages, I noticed that in December of the first month and April of the second month, of second year, they actually did a very big increase, like 108 and 106%. But you see that in the last year, they're still growing a little bit with 102%, but you know, the growth goes down. So this is a very good time to sell your stock in this company. And I got this information just by simply getting a bill each and every month. What happens if you launch a product, launch a website, and you say, we have over 100,000 subscriptions, over 100,000 users. And I register, and I got a link back from click here to confirm your subscription. And it says, my website /user/57. I don't think you have 100,000 users if I see something like that. But let's say that I subscribe next month as well, and I see I've got user 62. And a month later, I got user 63. So with that information, I can conclude a lot about your company, or a lot about your product, etc. With this information, I can pretty much, well, not accurately, because I don't know this stuff, but somebody who really knows this stuff, they can deduce what's the profit of that company, what's the turnover of that company, etc., just by simple numbers. So, how do we avoid the German tank problem? How do we avoid that people know how much we can leak? Well, try to avoid sequential data. So like the primary keys, the auto increments, that's sequential. It's fine if you use it, please use it, but don't leak it to the outside world. Use different identifications. Some smart people say, I just add a random number to it. Random number between 1 and 10, but don't do that either, because a random number between 1 and 10 will ultimately just have steps of 5 statistically. So you still have sequential data. One of the things that you could/should use is UUIDs, for instance. They have many different options, many different benefits. Personally, I don't like UUIDs because they are too large and they are not really useful database-wise. I prefer time-stamped or time-based short IDs. It's a little bit slower than UUIDs, but they don't have the drawbacks of UUIDs. But the same thing. So try and avoid that sequential data. Okay, anyone learned something new today? Yay, cool. Let's go to the next one, confirmation bias. We're all prone to confirmation bias. And I have a hypothesis. My office is near a lake. And there's a swan in that lake. And of course I do a lot of work, so most of my time I'm just staring at the lake. And I see a white swan. And I got a hypothesis. And my hypothesis is swans are always white, because I always see a white swan. That might be true. So I'm trying to find evidence. And evidence is more white swans. I look around for, have you seen any white swans? And people say, yeah, I've seen a white swan. Okay, well, there you go. Swans are always white. And the more I'm looking for white swans, the more I'm confirming my hypothesis. The more I believe that what I think is really correct, because I'm looking for white swans. And that works perfectly until this one. And this is a problem with confirmation bias. What we do is we try to confirm the things that we already know. But in fact, what you should do is try to disprove what you already know. But that's not something that's built into our brains. We like to confirm things. We don't like to disprove things. There's a scientific experiment, a game, if you will, and that consists of 3 different numbers, 2, 4, and 6. And those numbers can range between -infinity to +infinity, but they're whole numbers. The thing is, you have to find out a rule. These numbers follow a certain rule. That can be a very simple rule, that can be a very complex rule, but there's only one rule that those numbers will follow. Now, your job, if you want to take it, is figure out what that rule is. And to figure it out, you can tell me different numbers. And from those different numbers, I tell you if they adhere the rule or not. Now, the thing is, if you have an 80% or higher certainty that you know the rule, you can tell me the rule and I can tell you if that's correct or not correct. So it's a fairly simple game and you can try as much as possible. I don't give you the answer, because if you want to try it, we can do it later on as well. So I don't give you the answer, but I tell you that only 21% of the people will get it right. And this is not because it's a difficult game, but people try to confirm what they already know. Another thing, which is a sort of kind of, well, the thing is, and I already basically spoiled the game, don't try and confirm what you already know. Try and disprove again. You know, look for black swans or anything but white swans instead of looking for white swans. Confirmation bias is everywhere, and you probably use it in your daily work as well. How many of you use test-driven development? That's not a lot. How many of you write unit tests? You're lying. A lot of people write tests after the code, meaning they're trying to prove that the code is correct. I don't want to prove the code is correct. You're a developer. I assume you write correct code. I want you to disprove the code. Write a unit test to disprove your code. If the tests don't fail, then you have found out that you can't disprove your code. What you do with test-driven development, in my opinion, is you write your test first. You try to write, what can I make, how can I make my code fail? And then I'm going to fill in the code. And if the tests don't fail, then at that point, you basically have created code that can't be disproved by your test. There's another game, and this one we will do. It's sort of kind of related, which is this. There's one simple rule. If a card shows an even number on one face, then its opposite face must be blue. Now the thing is, how many of these cards follow these rules? You can turn over cards, but how many cards do you have to turn over minimum? Well, the thing is, if we try to do this, if they actually did this with the test panel, and only less than 10%, 9 point something percent, got it right. So that's not a lot. It's a real simple rule, and they just have to figure it out, but they can't. Only less than 10%. Developers and people with math skills and everything tend to be a little bit better. They tend to score a little bit higher, but probably 90% of you will fail this test. So what we do is we do a different way. We basically have the same assignment, the same rule, but we put it in a different context. And if there's a context related to conferences and PHP developers, I think beer. Somehow. I don't know why, but somehow I think beer. So what I've done, I rephrased the question. I said, if you drink beer, then you must be 18 years or older. So how many of these cards follow that? If you drink Coke, do we care if you are 18 years or older? No. So you don't have to turn over that card and to see what's on the other side. If you drink beer, do you have to be 18 years or older? Yeah. So we have to turn over and to see what's over there. So we have to turn this one over. If you're 35 years old, who is 35 or higher? Older? That's not a lot of people. Oh, we're the old gang. The old schools. Okay, if you're 35, does it matter if you drink beer or Coke? No, so we don't have to turn over that card. If you're 17, yes? Yeah. So we have to turn over these two cards. And I can guarantee you that almost 100% of the people get it right when it comes to beer. Very strange. But this is exactly the same question, exactly the same thing. This is called cognitive adaptation for social exchange. And this is a really fancy term for put something in a context that somebody else understands. For instance, try to place your technical problem, and we all have technical problems which we have to explain to managers and directors and CEOs and everything. Try and put them in a more social context. What I do often is use the context of building a house. So there's a customer and he's complaining about some button being red while we're still building the ground for an API system, for instance. I'm saying, okay, well, you can discuss, basically what you're doing is discuss the colors of the curtain while we're still building the foundation of the house. So let's focus on the foundation of the house. And then after we put on the walls and we put on the floors and everything, then we can discuss the color of the curtains. And that people get. But if you talk about APIs and CSS style sheets and front-end developers, and you already lost them most likely. So try and put your technical problem into a social context. That means for managers, just use very, very small words. So let's go back to that same question again. If a card shows an even number on one face, then its opposite face must be blue. Should we turn over the 5? It's not an even number, so we don't care. The 8. Yeah, because it has to be blue on the other side. The blue one. No, because it doesn't matter. We only said that if it's even, it has to be blue, but others could be blue as well. Sorry. You haven't seen that one? The green one. It's a trick question. The green one we have to turn over because it can't be even, because it has to be blue even. So we have to turn over that one as well. And now everybody gets it. So by just placing it in a different context, you can make problems much, much easier. This is what we do with basically TDD. And I'm not a huge fan of TDD, I'm sorry, but it's one of the things that makes it easier for you to do. Same with DDD, you put things in a different context, in a domain context, that your managers, that your customers, product owners actually get. Okay, next one, the birthday paradox. That's, I think, a more generic one. People have heard about the birthday paradox? Most likely, right? Okay, the birthday paradox is this. There's a question. I assume everybody has a birthday, right? Yeah? Somebody doesn't? Okay. what is the chance of how many people do we have to get into a room to have a more than 50% chance that two people share the same birthday? And a lot of people will go thinking, okay, so let's assume there's 366 days in a year. So divided by 2 is 183, 50% chance, so 183, 184-ish, right? That sounds about right. But actually it isn't. It's only 23 people. So we have more than 23 people in this room. But if we had only 23 people, there's a 50% chance that two people share the same birthday. If you have, I think, 57 people in the room, I think there's a 99% chance that you share the same birthday. But 23 people to get a 50% chance, people don't believe that. They think that's not a lot. That can't possibly be right. And that's the paradox. It's not a mathematical paradox. It's not something that contradicts itself. But it's people don't believe it. How can this be? We need 366 persons to get 100%. Well, depending on leap year, of course. So 50%, 23 people, 100%, 366 people. So that's a huge difference. The thing is, with the birthday paradox, collisions occur more often than you realize. For instance, hash collisions. We all use hashes on a daily basis, and normally we use hashes for encrypting, or at least hashing stuff, passwords and stuff. But hashes are useful for much more things. And hash collisions is something where this birthday paradox comes into play. For instance, if I have a hash value of 16 bits, which nowadays isn't a lot, but it used to be like the standard, you only need 300 elements to get a 50% chance on a collision. So if you use, for instance, CRC32 or CRC16, for instance, which was a long time ago standard, then you need only 300 different elements to get a 50% chance of a collision. Nowadays we use things like MD5 and SHA-1 and SHA-512, etc. Those numbers are way, way, way too big, but they're still prone to the birthday attack. So it means that their space, their key space, is much less than we think. So we don't get a lot of collisions, but nowadays we can collide things like MD5 without any problems. There's even collisions with SHA-1. So this is why Git is actually now trying to move away from SHA-1 to other different kinds of hashing algorithms to make sure that we don't collide and people don't use the birthday paradox to, do some nasty stuff with it. Here's the thing, random int 1 to 100,000. So this is the only PHP I have in this presentation. How many attempts do I need to get a 50% collision? How many do you think it's 1,000? How many 2,000? More? 5,000? Sorry? 6,000? No, less than 1,000. Yeah, it's 117. You can try it, if you have time in the next slot. Just try and create a simple program, and you will find out that almost 50% of the time you will get a collision, or 50% chance of a collision, by just selecting 117 elements. This is the birthday paradox. Anyone realize this? That this is not a lot, right? So watch out for using too small hashes. Most likely in the field that we are working, we're working with maybe MD5s, but SHA-1s and SHA-512s and everything, so you're probably okay with there. But if you use smaller hashes, watch out for that. Also watch out for unique data, because your data isn't that unique as you might think. That means that your data might be less protected than you think, because you think, well, I hashed it and so this hash is unique, so there's no other thing that is the same thing as our hash. Well, actually it might be, you just don't realize it. Okay, let's go to quantum physics. So how's the conference? Yeah, you know, we did a presentation about tap versus spaces, and we did a presentation about quantum physics, so yeah, okay. The Heisenberg uncertainty principle. This is not something from Star Trek. This is also not about crystal meth. Although if you're interested, my car is downstairs. This is about this formula. The variance of a position multiplied by the variance of the momentum, which is mass times velocity, must be greater or equal than a number, h bar divided by 2, which is a Planck constant. Anyone any questions about this one? Okay, I'm not going to go into details because I don't get the details, but basically it's about this. Suppose I have a tennis ball, and I throw that tennis ball at a certain direction and a certain force. I know exactly the trajectory, I know exactly where it lands, I know exactly how many times it bounces. I can all calculate that kind of stuff. That stuff is deterministic. If I do it 10 times, it does 10 times the same thing, considering all inputs are the same. And this works for tennis balls. This works for small tennis balls. This works for ping pong balls. This works for even molecules. But if you go further down into atoms, you go to electrons, you go to the nucleus, you go to protons, you go to neutrons, and even deeper you go to elementary particles. And the thing is, these things don't behave as we perceive in our daily life. Because you cannot say there's a certain particle at this certain point. You cannot say that. It's not exactly here. It's most likely to be here, but it's not 100% certain it's at this spot. There's a variance in where it might be. And it's too difficult to explain because I don't get it myself. But it's basically about statistics. If there's a particle, there's a chance that it's between here and here. There might be a chance that it's here or here, but that's less likely. There's a chance it's here or here, but it's even more less likely. It might be even on the other side of the universe, which is very, very unlikely, but statistically not zero. So this is what we call with the variance. So the more precise we know where that particle might be, the less we know about the other property, namely the momentum. Where does it go and how fast does it go? And what Heisenberg says is, well, first of all, you cannot know anything for 100% certain, because if the variance is 0, like you know exactly where it is, then something multiplied with 0 is 0, and it can't be 0. It must be at least this number. It's a very small number, but considering we have small particles, this number really adds up. So it can't be 0. There's always room for some variance. And the more you know about one property, the less you know about another property. So you know either one a lot, or both, you know, on average a little bit. So what's this about? The thing is, the more precise you know one property, the less you know about another. It's about trade-offs. If you come to me and say, listen, we need to go to a new framework. We need to go from our legacy code to Symfony 2, for instance, or Symfony 3. And you have a whole list, this is why we should do it. I don't honestly care about why we should do it, because those are the easy things to find out. Tell me why we shouldn't do it. Because we can say, okay, listen, this is a very good framework and it's, you know, flexible and everything, but there are trade-offs. Trade-off might be, well, people have to learn Symfony. It's a very small learning curve, but it's a steep learning curve. It means we can't do certain PHP versions anymore because we need to increase our PHP version, for instance. So there's always trade-offs. There can never be no trade-offs, because that's pretty much our nature. Heisenberg says there cannot be any trade-off. There must be trade-offs. There cannot be no trade-offs. So if you're going to say, listen, this is very good because this, and this, first of all, confirmation bias, because you're looking for things to confirm what you want to know. But go the other way around. Try to disprove. Why should we not use Symfony 2? Why should we not use this framework or this application or whatever? And if you have a list of a small list, because you can't find that many things, then you can make a good decision. So if you do something, try and figure out why you should not do it first, because that's the hard part to figure out. And that's the thing that most people will actually fail to tell people about. This is also not about observing. A lot of people say from, oh, Heisenberg, yeah, that means that if you look at something, then you will change it. Well, sort of kind of true, but this is not about observing an element. This is what we call the observer effect. Has anyone heard of a Heisenberg? It's not really that common in PHP, but if you do more low-level languages like C, for instance, there's a lot of time that you find a bug in your code and you try to debug it, and while you debug it, that bug will vanish. And then you stop debugging it, and then the bug will come again. So the fact that you are debugging the bug will fix the bug. Try and get that one straight. So this actually happens, and this is called a Heisenberg because of the principle. So it's a wrong term. It should not be called Heisenberg, but it should be called the observer effect bug. But that's less sexy than Heisenberg, I guess. So they call it Heisenberg. Okay. Anyone questions about quantum mechanics? Okay. Let's go to the next one. This is a fun one. Benford's law. Anyone heard about that? Okay, cool. So some people. Benford's law says numbers beginning with a 1 are more common than numbers beginning with a 9. And it goes away. So less common with 2, less common with 3, etc., all the way down with 9. And this is a natural occurring phenomena. This is default behavior for the natural numbers. And this is the actual formula for Benford's law. So you can write it down if you want. But basically it says if you have a collection of numerical samples, for instance, the top 100 cities, most populated cities in the world, or the longest rivers in the world, etc., then those numbers will start most often with a 1. So 1001 or 1024 or 11 or 117, etc. And less starting with a 2, 27, 216, etc. And this is a very strange phenomenon because nobody really can explain it. Everybody's like, well, yeah, that makes sense. But if you think about it, it actually does not make sense. And I tried it, like, okay, so maybe they used confirmation bias and they used only examples that fit their goal. So let's try it with something that I have control over. So what I did is I was working in a framework in the Symfony 2 project. And I thought, okay, well, let's go to the framework and let's find all the PHP files and see how long they are. So this this command line, you can actually run it in your own source code. It will actually find all the PHP files, find the line length, or find the length of the number of lines, and then cut away the first number. And if I do that on the Symfony 2 framework, I get something like this. So there are 1073 files that starts with the number 1. That could be 13 lines in the file, could be 117, could be 1316, etc. But the more you go down to 9, the less files they start. So I was like, okay, so that follows Benford's. That's pretty okay. I thought, okay, well, let's try some other frameworks. And I did that. I did it with a few. With Symfony 2, Laravel, Cent, Framework 2, and Cake PHP, because those are the only ones I could think of at that point. And I put them in the graph, and I get something like this. And notice that there's a blue line in between, and that blue line is the Benford curve. And pretty much all frameworks follow that Benford curve. The only exception, real exception, is Cent Framework 2. And I always thought there was something shady with Framework 2. So that's my suspicion confirmed. But there's something here like on the 5, there are less files starting with a 5, and there's a little bit more starting with a 1. But this information can tell you something about the natural process of numbers. Why are there less files starting with the number 5? There might be a reason, might not be a reason, might be just statistical flux, but can be a reason. The thing is, these are occurring to all natural numbers, including things like your bookkeeping, for instance. If you have a standard bookkeeping, it will probably follow Benford's law as well. I know it, the IRS knows it as well. So what they can do, and I think they do it in Netherlands as well, they have all kinds of different checks to see if somebody tampered with their tax incomes and everything. And if the numbers you send over does not adhere to the Benford's law, then they probably say, okay, well, so it's probably tampered with. Doesn't have to be, but it might be. So it's one of the triggers to make sure that to see, okay, well, let's take this one out of the pool and see if what happens. Why are the numbers there? Why is there a spike in the number 4, for instance? Because you have changed some 1s to 4s, etc., and now things change. So the takeaway from this presentation, if you're going to cheat on your taxes, make sure you follow Benford's law. Any questions about that one? Nope. Okay, so let's go to another one. Bayesian filtering. Who has heard about Bayesian filtering? Okay, who has used Bayesian filtering? Okay, everybody should raise a hand because everybody has used Bayesian filtering. Bayesian filtering is basically spam filtering. Most spam filters will use Bayesian filtering. Bayesian filtering basically says this. What's the probability of an event based on the conditions that might be related to that event? In other words, what's the chance that a message is spam or an email is spam when it contains certain words? And Bayesian filtering can figure that out. It can put a percentage on that, like it's very likely that this message is spam because it contains Viagra, etc. And this is the actual formula, and I don't go into details but basically P, A, or B is, that's the probability event A considering event B occurs, PA multiplied by P, B, or A divided by P, B. Okay, so how does this work? Basically, it's trying to figure out the probability that a mail, a tweet, a comment, a review is spam or negative. How many of you host things like user reviews or guest books or use user input and put that on a website? So there's people there that well, Coolblue probably will do that. What you can do is say, okay, listen, every time somebody submits a review, an article review or comment on a website, we pass it through a Bayesian filtering, and if it's on a certain threshold, we put it in moderation. If it's below a certain threshold, then we just post it on the website. So moderating a lot of reviews will be actually less user intensive. So let's try that with an example. And this is an example. Suppose I have 50 different comments on my website, and 10 of those comments are marked as negative comments. Your product sucks, etc. 25 of those 50 comments use the word horrible in it. So that means that there's a lot of positive comments that still use the word horrible. And 8 comments are marked with the word horrible are marked as negative. In a Venn diagram, I get something like this. It's probably not on scale, but there are 10 negative comments, 25 horrible comments, and 8 overlaps. And if you put it in the formula, we get this. We get 0.8 multiplied by 0.2 divided by 0.5 comes to 0.32. So that basically means that there's a 32% chance that that comment is negative based on the fact that I used the word horrible. So using the word horrible in this case does not make it a negative comment. But we cannot use only one single word, hopefully. We have to use a lot of different words. And this is what we do with naive Bayesian filtering. We actually concatenate all kinds of different words. So horrible and all kinds of negative words, and if you put it over there, we get into a certain percentage, and then we can say, okay, if it's above 80%, then we put it in moderation, and if it's above 95%, then we just delete the comment, because it's probably not good. So you can do that with something called naive Bayesian filtering. This is actually pretty easy to create in PHP as well. It does not take a lot of math, it does not take a lot of effort. You can do it quite easily in a few lines of PHP code. And it works pretty well. You have to train your set to say what is negative and what is positive. And if you feed it, this is why your spam filters only work after a certain amount of messages. So you have to mark messages as spam, and then it will update your Bayesian filtering to say, okay, words in there are more likely to be spam words than other messages. What you want to do is you want to filter stop words as well, because there's probably no point in using stop words. Make sure that negatives are handled properly, because not great is not a positive thing, it's a negative thing, while great alone is a positive thing. And bonus points if you can spot sarcasm. I don't think anyone has got that. But okay, there's another thing as well that's related to Bayesian filtering. It's called collaborative filtering. Has anyone used Apache Mahout? Okay, that's an awesome application. Basically, it says if a user likes product A, B, and C, what is the chance that that user likes product D as well? And it uses all kinds of feedback on products and other users, and it put it in one large Mahout pool, and it will go out, oh, well, if it likes A, B, and C, then there's an 83% chance that it likes D as well. So you can actually create very simple recommendation engines based on input from other users. You can actually use things like friends and all kinds of networks put together. You put it in Mahout, and out comes all kinds of recommendation engines. Basically what Netflix does in their system, you know, because I watched this show, and this show, that means I probably like that show as well. So you're actually training Netflix. Every time you watch a show, you are training Netflix into trying to figure out what you like. So this is why you should watch Netflix a lot, because you get better recommendations. Mess up your training data, and nothing can save you except a complete reset. I have children. Things like The Fall and Twin Peaks, yes, sure, I like them. But there's things like Team Hot Wheels and Timmy Time. It wasn't me. Really. So that messes up your training set. So this is why you have different profiles, just to make sure that if you have kids, put them in a different profile, please, because otherwise your recommendation will be awful. Trust me. Okay, any questions? This was the last one as well. I hope you enjoyed some of them. I hope you can put them into practice as well, especially confirmation bias. Try and figure out what you are doing in confirmation bias. If you have any, if you want to do the game as well, the 2-4-6 game, I'm over here as well, so I can try and see if you are part of the 21% or if you're part of the other ones. Okay, thank you.